Okay, so one thing that I would like to point out for Galton-Watson branching process is the following. This is a Markov chain, of course. It's starting from one particle and then with this transition probability. Now, one thing is clear is that, say, if I is 0, so in other words, if xn takes the value 0, then obviously xn plus 1 has no other choice but to take the value 0. Because if I is 0, then this random variable becomes 0, and therefore the only value it can take with positive probability is the value 0. So what this says is that once the colony of bacteria or the system of particles dies off, that's the end of it. And from then on, the value of xn is going to remain at 0. So this statement can be restated in the language of Markov chains as 0 is an absorbing state for branching process. We'll formally give this definition, and this would be an example, but I just wanted to point this out. Now, of course, question that appear that is natural is, when does it happen? When will a Galton-Watson branching process become 0 eventually? Now, this question has a very easy answer, which we are not going to cover at all, but you can look it up in various places, including the Adventures in Stochastic Processes. By the way, you must have downloaded the book by now. It's going to be important for this part of the course. So, the summary is very easy. It's just given by one parameter, namely the progeny mean. You have this progeny distribution. Compute the mean of this distribution, expectation of this distribution. If the progeny mean is strictly less than 1 or equal to 1, if the progeny mean is less than or equal to 1, then xn becomes 0 eventually. So in other words, the colony of bacteria dies off, which can be a good news if it's a bad bacteria. On the other hand, if the progeny mean is strictly bigger than 1, then xn does not die off. Not only that it does not die off, it actually grows exponentially. So you see an exponential growth. So in some sense, we are talking about this exponential growth and so on these days. And we're talking about this R, this random variable R that, how many people one can contact and so on. It's nothing but a progeny mean in a very simplistic sense. If you just think of a simplistic possible model of spreading of any disease, okay, then very important object is this progeny mean. Anyway, this is just I wanted to make a relevant comment. That's all. It's not that we are going to discuss this in details or anything. Okay, so then I'll revisit 3 of the examples of random walks on groups that I stated last time. I didn't give explicitly the transition probabilities in those cases. We are going to do that quickly. The first one is a simple random walk on ZD, in which case you start at the origin and always move to one of the neighbors in the graph. So in ZD, you'll have 2D many neighbors. So in Z2, in this picture, you have 4 neighbors. So namely, for wherever you are, you can either go to +1 or -1 in each of the coordinates. Okay? So that gives you, there are D coordinates, so that gives you 2D many neighbors. Now, this Markov chain has initial distribution delta naught, which is because it starts at the origin. And the transition matrix is just 1 over 2d whenever j and I are neighbors. So when are j and I going to be neighbors? If the difference of j and I is either e1, e2 up to ed, one of the random variables, one of the basis vectors, or minus e1 minus e2 up to minus e2. One of these 2d possibilities are there. In other words, Pij would be 1 over 2d if the absolute difference between j and I is one of the basis vectors and 0 otherwise. And this is obvious from this picture. From 0, 0, you can only move to one of the basis vectors. So these are the basis vectors or the negatives of their basis vector, of those basis vectors. So this is e1, this is minus e1, this is e2, and this is minus e2. So from 0, 0, you can go to any of these 4 places. So in general, for any point, you can go to just for one of the 4 options given by this expression here. Now, in case of the discrete cube, z to power d, you have d many neighbors. So for example, when d is equal to 3, this is a picture, the origin has 3 neighbors, okay? Namely e1, e2, and e3. Why don't we have minus e1, minus e2, and minus e3? Because here the addition is modulo 2, so minus e1 is same as e1. Minus e2 is same as e2, and so on. So therefore, we don't have those. So this is the difference between zd and z2d. The number of neighbors is half of what it used to be in zd. So this is a Markov chain whose initial distribution again is delta naught. So it starts at the origin. And the transition matrix Pij is given by 1 over d, whenever j minus I is one of the basis vectors. This is something we stated last time. I just wanted to state the difference of this and the previous one. So the previous one, you had an absolute value, and therefore, for any, if you're at I, you have 2d many possibilities. You can take a step e1, you can take a step minus e1, you can take a step e2, or you can take a step minus e2, and so on, all the way up to ed and minus ed. 2d many options. Here, you have only d many options, because minus e1 is same as e1, essentially. Okay, so you can either take a step e1 or take a step e2, all the way up to, you can take a step ed. So that gives you this transition probability. In the simple random walk on F2, this is a Markov chain that's on F2 with initial distribution delta E. So this is the distribution on F2 that puts mass 1 on the empty word or the identity element in the free group. And the transition probability matrix PUV is given by. So any point is always moving in this picture, as you can see, always moving to one of its neighbor at random, right? So say B will move to either BA or BA inverse or B square or E with probabilities 1/4 each. So therefore, if in the Cayley graph 2 elements are neighbors, then the transition probability is 1/4. Otherwise, the transition probability is 0. So therefore, PUV would be 1/4 whenever U and V are neighbors in the Cayley graph, which essentially means whenever U inverse V is one of the standard generators. So whenever U inverse V is either A or B or A inverse or B inverse. Okay. So from U, essentially, you can only go to either UA or UB or UA inverse or UB inverse. That's what this means. Okay. With probability 1/4 each. And of course, no other movement is possible. So this is the nearest neighbor. This is the nearest neighbor. This is the nearest neighbor random walk on this graph. And not only its nearest neighbor, it's also simple in the sense that all of nearest neighbors have equal probability to jump. So essentially, any element will jump to one of its nearest neighbor with equal probability. So that's why it's a simple random walk. So if you see, all of these 3 examples have the following thing in common. So if you don't know what is a Cayley graph, you can ignore this part of the lecture. It's not going to be important at all for our course. But if you do know what is a Kelly graph of a group, then what this means is that all of these are simple random walk, because these are not just simple random walk on the group, it's actually a simple random walk on the corresponding Kelly graph when you take the generator, set of generators to be the standard one. And in order to make it a graph, you have to take the symmetric set of generators, as you perhaps know. But you take a standard set of generators, look at the Kelly graph, and then start at the identity element, and then just take simple random walk in this Kelly graph, in the sense that you, at every time you start from the identity element, move to one of the neighbors at random. Wherever you are, you move to one of the neighbors in the Kelly graph at random, and so on, uniformly at random, and so on. So essentially all of these simple random walks are actually simple random walks on the corresponding Kelly graphs, where the set of generators is the standard set of generators. Okay, but if you don't know what is a Kelly graph, don't worry about it. It's enough to understand these three examples for this course.